friends, welcome to Dream Academia. For those who don't know what is Dream Academia, let me tell you that Dream Academia is a platform where we are providing quality education with the help of the latest technology. Basically, we are making some educational content for those students who are preparing for entrance examination like JEE Mains, JEE Advanced, WBJEE, NEET, and other state competitive exam like that. Again, we have a Telegram channel. So if you have any doubt on your studying or if you have just stuck on a problem, you can post there and we will try our best to resolve your doubt. And the link of the Telegram group is in the description box, so you can just check it out from there. Okay, so before we begin, let me give a brief introduction about myself. So I am Tapas Mandal. I am currently a BTech student from Jadavpur University and I am pursuing my mechanical engineering. Okay, so this is my Twitter handle and you can just follow me there, and this is my Instagram, you can follow me there also. So today we will study gravitation. We'll discussing the topic gravitation today. So as you might know that this chapter, gravitation chapter, is a very important chapter from the point of view of your WBJEE, JEE Mains and board exam as well. So this, if you prepare this chapter well, you can get a good idea about the chapter in your class 12, that is electrostatics. So you have to have a good comment on this chapter. So we will see some formulas and numericals after that, so that our concept can be clarified easily. Okay, so first of all we'll see the gravitational force. So if there was two body, m1 mass and m2 mass, so they attract each other with a force of gravitational force, and the value depend on this term. Okay, so here this g is a gravitational constant and its value is 6.67 into 10 to the power minus 11. Okay, and this gravitational constant is a universal constant. This value doesn't depend on the medium or anything else. It is a constant. It is a universal constant. Its value always remains same. Okay, and some properties of this force are like, this is a central force. Okay, so this mass and this mass attract each other toward their center. Okay, and this is a conservative force, and it is always attractive force. This is attractive in nature. Okay, it doesn't repel. Now gravity field. Gravity field is a vector quantity and it is defined by the gravitational force per unit mass is called the gravitational field intensity, and it is defined by F upon m. Okay, so this body, and there is a big body right here, so the force of the gravitational will be let consider the distance between these two is r, and this is the force on this body and this body as well. So if you have to find out the field on this body, you need to divide this force by m, so it will be coming out to be gm upon r square. So this will be the field at this point. Now we will see some field due to the presence of different body at a point. So if you don't written down on your paper or anywhere, so you can just pause the video and write down the formulas for your convenience. Okay, so first of all, the field due to presence of a body, presence of a mass. So here is a mass m, and the field on that point due to the presence of this point mass will be gm upon r square into r cap. So here r cap is given because this field is toward the point mass from this mass. Okay, so that's why this r cap is given, because we are measuring from here to the point was. So that's why this r cap is given in this direction. Okay, and again we have the field due to circular ring, and it is formulated by these stuffs. Okay, and the diagram is not given, so I am just drawing the diagram for you. Here A is the radius of the ring and r is the distance between the center of the ring to the point. If you didn't write those stuff, so you can just pause the video and write those stuffs on your paper, so that before you going to go to exam, just see those stuffs and it will be good for you. Now moving next, we can again formulate the field due to a uniform disk. So earlier we have seen the field due to a uniform ring, and we are seeing now for a uniform disk. And this is same as the uniform ring, but the derivation is a bit difficult here. We're not going on that way because it is a crash course, so we're not going there. If we have a hollow sphere, the field inside any point of the hollow sphere will be zero. Inside any point of the hollow sphere will be zero, because this body is field attracted by there, there, and from everywhere else. So that's why the total field get cancelled from there. So that's why the field on inside the point is zero. On the surface, the field is gm upon r square, where r is the radius of the hollow sphere. And outside the surface, the field is gm upon r square, where r is this radius. This radius means the distance between the center and the point. Okay, so let the point is P, and this is the field at point P. Okay, and if we draw the graph, we'll see that this is E and this is my distance. Let's see, say this is X. So from 0 to R it is 0. Okay, from 0 to R it is 0. So let is the another color. Let use black. From 0 to R it is 0, and in R, where X equals to R, it is gm upon r square. And from there it is from there it decreases. So this is the graph. Okay, now let's move on to the next topic, and this is the field due to a solid sphere. So similar, but the inside the sphere, the field is gm r upon r square here, not 0. Okay, so inside the sphere, the field is gm r upon r square. This is P, and the distances are here. Okay, and on the surface the field is gm upon r square, and outside the surface it is gm upon r small r square. Okay, so if we draw the graph, we'll get, let's say this is r. From 0 to r it rises. Okay, at r its value is gm upon r square, then it decreases with a parabolic curve. Okay, so this is the graph of field to a solid sphere, due to a solid sphere. Okay, now gravitational potential. Gravitational potential is basically the amount of work done to bring a unit mass from infinity. Okay, so there is a mass which is at infinity, and this point, from this point, so gravitational potential is basically the total work done need to bring this body to that point under the influence of the gravitational field of the mass m without changing its velocity. So we have to bring this body to that point m without changing the velocity. So in that process the amount of work done need, so that will be my gravitational potential, and it is formulated by this. Again, like the gravitational field, we will not calculate, we will just see the formulas of gravitational potential due to different body. So for ring it is formulated by this. Okay, there is a ring, and from the axis uh, from the axis, from any point on the axis, the potential will be this, and the radius of the ring is a here, and the potential due to a cell will be on inside the sphere, it will be like minus gm upon r. On the surface it will be again minus gm upon r, and outside the surface it will be gm upon capital small r. Okay, so the graph will be like, it will be in negative direction. Okay, since there is a negative sign. So firstly from r it is same, which is gm upon r. Okay, this is minus gm upon r, and after that it is decreases. Okay, so that will be my graph. Again we have potential energy due to a solid sphere. So inside a solid sphere the potential energy is formulated by this term, and on the surface this is defined by this, and outside the surface it is defined by this. So we'll see the graph here. let's say the point is r. From 0 to r it will follow a typical graph. It will be like, and after that it will have a value of, on r it will have a value of gm upon r, and after that when it will be outside the surface it will follow the typical graph of like this. Okay, now we have the variation of gravitational acceleration due to height. On a height of h, the gravitational acceleration will not same as of the surface. It will be formulated by this. When h is much less than r, we will use this formula, and when h is comparable to r, we will use this formula. Okay, and the variation of gravitational acceleration to depth is formulated by this, and variation of gravitational acceleration in the rotation of the earth is defined by this. Here omega is angular velocity of earth, angular velocity of earth, and theta is the angle made by the point with the equator. Okay, now orbital velocity. So there is a earth, right? Consider this to be earth, and if you throw a ball from there, let's say this is you throw a ball and it will just drop on that point, and if you throw with a much more velocity it will drop further, it will go further. And if you throw this ball, if you have enough power to throw this ball with much more velocity than this, it will revolve around the sun, revolve around the earth like this. Revolve around the earth, and the velocity will be g root over of gm upon r. And here we have escape velocity. Escape velocity is the velocity that we need to give so that a body doesn't return back to the earth's surface. So this is defined by escape velocity, and it is formulated by 2 root over 2 gm upon r. And again for earth, basically for earth it is 2 gr, since gm equals to, this is since gm upon gm equals to and this is for earth. Okay, for earth only. For earth only. The kinetic energy of a satellite revolving around a planet of mass m is formulated by gmm upon 2r, and the potential energy is minus of gmm upon r. Now moving lastly, we have Kepler's law. The first law of Kepler says that the planet revolve around the sun in elliptical orbit with the sun at one of the focus. So it basically says that every planet revolve around a sun on an elliptical path, and the sun remains on one of the focus of the ellipse. And the second law says that a line from the sun, okay, so line from the sun, okay, so this is, let's say this is my earth. This says that the line from the sun sweeps equal amount of area on equal interval of time. So it will sweep equal amount of area. So on a, let's say on a particular interval, it sweeps a area of this. So in order to maintain that formula, it have to sweep more amount of, it have to sweep that equal amount of area in this case also on a same time, same interval. So it have to move faster on that peripheral region, that of this aperian region, okay. And the third law says that the square of the time period of the planet is proportional to the cube of the semi-major axis of the elliptical path, that is t square varieties r cube, okay. Now we'll see some numerical from this chapter. So firstly we have this numerical: two particles of mass m1 and m2 approaches each other due to their mutual gravitational attraction only. Then we have acceleration of both the particles are equal. So it basically says that we have a particle of mass m1 and m2. So the force on that body will be what? G m m1 m2 upon r square, whereas the r is the distance between these two, okay. So first option says that the acceleration of both the particles are equal. So acceleration of this particle will be what? Acceleration of m1 will be f upon m1. This is gmm square upon m1. So this is gm2 upon r square. And acceleration of m2 particle will be so we are seeing that the acceleration is not same, so option A can't be true. And here it says that the acceleration of the particle of mass m1 is proportional to m2. So we can see that here it doesn't depend upon the acceleration of the particle of mass m1, is doesn't depend on the mass m1, so it is false. Acceleration of the particle of mass m1 is proportional to m2. So since it is proportional, here we can see that. So this is my right answer. Now a satellite has a kinetic energy k and potential energy v and the total energy E. Which of the following statement is true? So we know that kinetic energy of a satellite is what? Kinetic energy k is gm capital M upon 2r. Potential energy v equals to minus of g small m capital M upon r. And my total energy E is k plus v. This is going to be g small m capital M upon 2r minus of g small m capital M upon r. That is gm and this is coming out to be minus of g. So this is nothing but what? Minus of k or v by 2, right? So E equals to, what will be my answer? equals to minus k by 2, this is wrong, plus k by 2, this is also wrong, k equals to v by 2, no, this is also wrong, and from there we can say that minus k equals to v by 2, or k equals to v by 2. So option A is my correct answer. Now moving to the next question, we have a dimension analysis question. So here we need to find out the dimension of the universal gravitational constant G. We know that F equals to G into m1 into m2 upon r square. So G equals to m1 into m2. Here the dimension of F is, okay, now dimension of G is m L t to the power minus 2 into L square upon m square. So we will get m to the power minus 1 L3 t to the power minus 2. So this is my dimension. Okay, so option B is my correct answer. Now moving next, here it is says that when a body moves in a circular orbit, its total energy, we know the total energy. Okay, total energy is equals to total potential energy plus total kinetic energy. Total potential energy is equals to G m capital M small m upon r, and the total kinetic energy is G small m capital M upon 2r. So we have G small m capital M upon 2r. So it is coming out to be negative, so that's why my answer is option B. Now moving to the next question, here it is given that assume that the earth rotates in a circular orbit around the sun in 365 days. Okay, so t 365 days firstly, and if the mass of the sun gets double but the radius of the orbit remains unchanged, the length of the year would be approximately what? So we know that t, that is the time period, equals to 2 pi r upon the velocity. Okay, and we know the orbital velocity is v naught equals to root of g capital M upon r. So t equals to 2 pi r so t equals to 2 pi r3 by 2. So from there we can say that t is proportional to r to the power 3 by 2 on root of m. Okay, so here t1 upon t2 equals to r 3 by 2 upon root of m1 into root of m2 upon r2 3 by 2. Here r1 and r2 is same, so we can just neglect that. m2 upon m1, t1 upon t2. So t1 upon t2 equals to, and it is given that the mass of the sun gets double. So finally the mass of the sun get double, so it will be 2 m1 upon m. So t1 upon t2 will be root 2. Okay, so we are just writing here t1 upon t2 equals to root 2. So t2 will be t1 upon what, t1 upon root 2. And firstly we have what, firstly we have the we have time period as 365 days. We have to find out the final time period when the mass of the sun get doubled. That will be 365 upon root 2. So approximately this will be 365 upon 1.4. so it is coming out to be, it wouldn't be more than 365, it is obvious, so we can neglect this two option from there, and it will be not closer to 138 as well. So this would be my correct answer. This will be my approximately correct answer. Thanks for watching. Stay safe and stay happy always. And don't forget that the pandemic is not over yet. So regularly wash your hand with soaps and sanitizer, wear a mask, and keep maintain the social distancing norms as far as you can. And anyway, hope you found this video useful, and if you did, give a thumbs up, and if you wanted to see more educational video like this, don't forget to hit that subscribe button. And if you have any queries or comment or question, feel free to leave it down in the comment section below, and I'll try my best to address them. So till we meet next, bye.